So you have to submit your project proposals today, and a lot of you sent me emails asking what should be in the project proposal, or people met me in person. And just a quick description of what I expect to see in a project proposal. All I want is to know what you want to do for your project. All I want to know is that you've thought about it for at least longer than 5 minutes. To the extent that you are able to write a paragraph of text about it. So you have to tell me what's your project, why is it interesting, why is it machine learning? I mean, you don't have to explicitly have these sections, but tell me why it's connected to the class, because it's easy to do a project that's not machine learning, and that is not very cool. So, and the point of this project proposal is not so much that, as I said last week, it's not so much that I'll hold it up as a contract. The point is, I get to know what you're doing, and then we'll have a conversation. Either I'll say, yeah, go for it, or maybe I'll say, let's change it, and we'll have a conversation based on that. Any questions? Oh, and the other thing is, please don't email it to me. Submit it on Canvas. You should be able to submit at this point. So, and only one submission per group is needed. Okay, if there are no questions about project, I'm going to move on. Going once, twice, 1.5. All right. So we're in the middle of our Perceptron lecture, actually coming to the end of it. And in the last class on Tuesday, we saw the Perceptron algorithm, and we looked at the mistake bound. So let me just do a quick recap of that. Remember that the Perceptron algorithm is an online algorithm the way it's defined, at least the version that we saw. And because it's an online algorithm, there are two phases. There's a prediction step and there's a correction step. A stream of examples come in. The algorithm looks at one example, and I call it xi, yi. It has a current guess for a hypothesis, which is basically a weight vector, because perceptrons learn linear classifiers. It uses the current weight vector and it takes a dot product of the current weights with the new incoming example and makes a prediction. How does it make the prediction? It just looks at the sign of that dot product. And then it gets the answer, the true label, yi, and compares. If there's a mistake, then it makes an update. And the nature of the update is additive. It just adds yi times xi to the weight vector if there's a mistake. That's pretty much it. It's one of the simplest algorithms that we can think of, and this is also probably one of the older ones. And yet it has this fantastic property in the form of a mistake bound. And we saw this theorem, and in fact we looked at the proof of this theorem in the last lecture. The mistake bound simply in English, not in English, in actual English, it says, if the concept is linearly separable, then the perceptron algorithm will learn the concept after making only a finite number of mistakes. And we went through the proof in some detail in the last class. Any questions about the mistake bound, the nature of the mistake bound, or the proof, or the algorithm itself? Yes?
I actually have a question about something else.
Okay.
Can you explain the difference between a linear threshold function and then like a plane versus an equation of a plane that separates the data? Are those the same?
They are the same.
Okay.
So a linear threshold function is simply a function of the form W transpose X plus B. Sorry, it's a function of the form the sign of W transpose X plus B. Okay, for any X. Now, because you know the equation of a line, it's just dot product W dot X plus B. And so that this means that the decision boundary is a line or a plane. So linear threshold units learn separators that are just hyperplanes, or they are equivalent to separators that are hyperplanes.
So if you, like when you ask that question in the homework, they just give you the equation of the plane?
Yes, or in this case, I don't remember how many dimensions you had, a line or a plane or some linear function. Yes. And yeah, that's the other the good thing you brought that up. There's a homework out in the wild, so I hope you guys look at it and not leave it for the last day because, you know, why? Also, you have to, this homework lets you explore two things. It lets you explore linear functions, linear classifiers through some simple examples, and also in the form of the perceptron algorithm and its variants. And it lets you explore the idea of mistake bounds or mistake bound algorithms. That's the second question in your homework. So yeah, please look at it, and if you have any questions about the homework, feel free to ask them as well. Yes?
Another question about the homework.
Excellent.
Number 2, it talks about a function that says, basically it describes a function that, I think what it's saying is that for every input, every element in the input space, there's some function that matches that exact input. If it gets that exact input, it's true, or else it's false. Is that what?
That's exactly what it is.
Okay.
So for every element in the input space, if that element comes in, this function says yes. Otherwise, it will say
so basically there's a function for every input.
yeah. Yeah. Is that your question?
Yeah, I think I had, so it's not talking about the individual coordinates.
No.
Like whether
No, the entire vector has to match. The entire input has to be identical. It's not about the individual coordinates. Yes.
So I'm running cross-validation with the perceptron, both the simple perceptron and the weighted perceptron. You mentioned to try to use values of R less than 1.
Mm-hmm.
I included values of R greater than 1, like 2, 3,
Sure.
4, and 5, and they seem to perform sometimes better.
Possibly. Yeah. I'm not saying they won't.
Is there a reason for the
So, in fact, that also goes back to a question that someone asked last class. So the perceptron algorithm, another way of thinking about it, is that it's actually stochastic gradient descent for some function. And if we want the guarantees of the stochastic gradient descent to apply, then the value of R should be less than 1, and it should be the sum of the squares of R over time should be less than, should not be infinite. Those guarantees don't apply only then, the convergence guarantees. So that's one of the reasons. And the other reason is so that you don't hit infinities eventually.
Because it seems like if you use a large R, then it kind of cancels out the fact that you're using a randomized weight vector.
Quite possibly, yes. It's entirely likely. So, in fact, mention it in your report if you do that. That, you know, the best R is not the one. I don't even know if this is right or wrong, but, you know, why not? Are there any questions about the mistake bound itself? Since we're talking about homework so much.
I had a doubt about when we're implementing and we have to try out different parameters, hyperparameters. So we're sampling the data for every 0 and 10, right? Like we take an average of hyperparameters over the training data, and are we doing it like that?
So,
is that okay?
I don't quite understand what you're saying.
Okay, so the idea is that we want to choose a few hyperparameters which we will use on the final test set.
Sure. Not on the final test set, which you'll use to train a classifier on the entire training set.
On the entire training set.
So since I don't understand your question, let me just tell you what you need to do.
Okay.
So let's take the margin perceptron as an example. There are two hyperparameters. In fact, you know what? Let's hold on to that question. I'll get to that. Can you bring it up again when I go over margin perceptron and towards the end of this lecture? Okay, but don't forget to bring it up. I'm going to take that as a sign that everyone knows what the mistake bound is. So you're all ready for a quiz if necessary. Okay, I see a lot of nervous people. No, I don't like doing quizzes. So anyway, no, I don't like being on your side of a quiz. So in any case, perceptron algorithm has a mistake bound. And the fantastic thing about this, and I said this in the end of the last lecture and I want to mention it again, fantastic thing about the perceptron algorithm is it doesn't matter how big your training set is. It doesn't matter if you have a million examples. After seeing these many examples, after making these many mistakes actually, not seeing these many examples, it's going to stop making mistakes. The size of your training data does not even factor into this equation, which is pretty cool if you think about it. It doesn't matter. I mean, it's going to stop making mistakes, and then your algorithm, it doesn't matter whether you run the perceptron algorithm longer or not, because you're done. Learning is over. There is a concrete point in your training cycle when you can proclaim that learning is over. Almost. If you knew the values of R and gamma, which we don't, so it doesn't happen in practice. So this is a good news, bad news situation. On one hand, in coming up with this mistake bound, we made no assumptions about the data, except that it's linearly separable. We made no assumptions that the examples will be presented to us in a favorable manner. It could be the worst possible sequence of examples, and still you'll make only these many mistakes. On the other hand, we make the assumption that the data is linearly separable, and unfortunately this is almost never true, unless you have a very contrived example. So then we have to come up with other techniques to deal with basically help the perceptron algorithm generalize better. And one of those tricks, and that's probably the most popular trick around, is called the average perceptron. And we'll be talking about the average perceptron right now, but I do want to just to give you a heads up. In the future, if you ever have to implement the perceptron algorithm, always implement the average perceptron, and we'll see what it is, and a couple of variants. Question.
So there's a question. It's related to question 2 on the homework. If every input is represented by a function that returns true for that input and false for others, then no function will produce the wrong answer. Is that correct?
I don't know what the wrong answer is.
It would probably take like 15 seconds for
Okay.
to respond.
So, because there's going to be a time delay, I'm going to keep talking. So, in the homework, every input point is associated with one function. And what that means is, remember that there's only one true function that we care to find. If we don't find that function, then the answer is wrong. Right? Is there any traffic on the...
He said he'll ask you in an email later.
Oh, okay, fine. Or even better, maybe post it on a discussion board so that others who have the same question will be able to see the answer as well. Okay, let's now move on to the last part of this whole perceptron lecture, where we're going to discuss a few variants of perceptron. Because this algorithm is so old, there are tons and tons of variants. So I'm not going to look at all of them, I'm just going to present 3. In the vanilla version of perceptron, I assume that there's an infinite stream of examples that keeps coming in. We have no control. But in practice, we only have a finite data set. So the first variant will be the one that is called the batch version of perceptron, where you have a finite data set and you want to learn a concept. Then we'll go to this idea of voting and averaging, which is actually a general trick that applies to many classifiers in general. And it just so happened that it was invented for the perceptron algorithm first, and it was as late as, I think, 1990s. And finally, I'll talk about something that you guys are going to be implementing in your homework, the margin perceptron. So let me start off with what I have come to think of as the standard version of the perceptron, and it's going to look very similar to the version of perceptron that you've seen before, except for a couple of changes. The first one is that we have a fixed training set. We only have those many examples, we don't have an infinite stream of points coming in all the time. And we have to make do with these examples as well as we can. Which means, you can't just do one pass over the data and hope that you're done. right? Because you may not hit the mistake bound if that happens. So what is done in practice is that this is the original perceptron algorithm. You just loop over the training set multiple times, again and again. So you have two loops. One which just, the outer loop is called an epoch. You have multiple epochs. You do one pass over the entire data, and then once that again finishes, you keep going again and again. So now the question is how many epochs and all that. We'll get to that in a bit, but I just want to remind you that irrespective of what the learning changes are, prediction is still the same. Finally, you just predict with the sign of w dot x. Well, was there a question?
Can you explain again why you want to do multiple runs over the same data? You said you wouldn't hit the mistake bound.
Right, so if you only have a finite number of examples, you'll probably not, the number of examples that you have might be less than the mistake bound, right? And so you mimic this fact that you have enough data by just going over the data again and again.
In a different order.
That's important. That's actually very important. So there are a few subtleties in this algorithm. The first one is this letter capital T. This is a hyperparameter, another hyperparameter, because we don't have so many. And this decides how many passes you make over the data. It's typically, you just fix it up front and you just live with it. And in practice, this number is not a large number. In many research applications that I've seen, typically we pick like a small number like 10 or 20 and that's it. You do a few passes over the data. Point that you made is actually very important. In practice, before you enter the inner loop here, at this point, you shuffle the data. And in fact, shuffling the data is crucial. I just didn't put it here because I wanted to draw an arrow on the slide. It's important that you shuffle the data, and very often not shuffling the data might give you suboptimal classifiers. The order in which the updates are carried out, it has to be randomized. And just wanted to remind you that inside each epoch, we're still doing the same thing. We pick a random example and check if there's an error. If there's an error, then we make an update, and the update rule is the same. Questions about this version of the perceptron? Yes.
How stable is it to noise and outliers?
This is actually more stable to noise. It doesn't care about outliers because there's no notion of an outlier in the mistake bound, right? Because if the data is separable, then you get the guarantees.
From a high level, how can you learn something more from something you've already seen?
Excellent point. If, let's say, that's a good point actually. Remember that you made a mistake on one example, let's say, and you make an update. There's no guarantee that after you made that update, immediately after that, you're going to be correct. Right? That's one thing. The other thing is, you make a mistake on one example, you correct it. Let's say you make a mistake, you update, and let's say just so happens after the update you are going to predict this thing correctly. Then you see another example, and that ruins the first one. So you want to keep going back so that it settles into some average good behavior. Yes.
So, for each epoch, what is 1 to 8? It's the different values of hyperparameters?
Which one?
For each epoch.
Oh, it's just that has nothing to do with it.
That's a sampling of the data set, right?
No. So the way it works is you have a fixed data set. Okay. You first shuffle the data and run the inner loop. So run this thing. Okay. Let's call that the inner loop. You shuffle the data, you run the inner loop. And then you shuffle the data again, you run the inner loop. And you do that t times.
So shuffling is just rearranging the order of the records in the same data.
Exactly. Yes.
Is our weight vector W, does that, since we're randomizing it, is that going to affect our optimal T?
No, actually no. If you do, because we are going to do so many iterations over the data, in expectation it's going to be okay.
Okay.
Yes.
Why do we need to shuffle the data?
Why do we need to shuffle the data? It just, okay, again that goes back to one way of thinking about that is, remember the incremental or stochastic algorithm that we saw for the least mean square? You pick an example, compute a gradient and go on. You pick an example randomly, right? Shuffling, and this, it turns out, is exactly stochastic gradient descent. For a certain objective, we'll see that maybe in 3 weeks. So for those guarantees to kick in, you need the examples to be chosen randomly. And shuffling is just a way of mimicking randomness.
So for the same set of data in a different order, you can get a different hyperplane each time. If you shuffle the order,
Possibly.
if it's the same order, you get the same hyperplane.
Yes.
You shuffle it, different hyperplane.
Possibly, but in expectation, if you do this enough number of times, it will converge on the same thing.
Now that the order of mistakes are important, is there any difference between just looking at the last mistakes and looking at the last few mistakes?
Or what does that mean?
I mean, when you want to update the W, you're looking at the output of the last mistake.
Right, of the current mistake.
Yeah.
Yes.
Or you just look at the
Oh yeah, so in practice, another trick that people use is you take a few small bunch of examples, not one, and use those mistakes to update, and that's called a mini batch. You take a small bunch, instead of picking one training example, you take say 10. Make an up, check for all those mistakes and make an update.
reduce the number of T. I mean, the
That might reduce the number, that actually tends to lead to convergence faster, yes. Other questions? Okay, so this is the usual version of perceptron that you see typically in papers, and when people say perceptron, you are expected to provide two parameters. One is the learning rate and the other one is the number of epochs. In fact, in your homework, I think in your implementation, I asked you to run your algorithm on one epoch and then run it multiple times. Okay, so here's another little, to motivate the second variant of the perceptron algorithm, let me slightly change gears. Let's say we see a sequence of examples. Let's say in the vanilla perceptron, not even in the batch version, in the online version of the perceptron, we see a sequence of examples. And let's say we don't make any mistakes, we've not made any mistakes for millions of examples, and we keep seeing them. And the algorithm is perfect. And then finally, you're almost done. You're going to claim that you're done just if you have one more example, and if this guy says yes on that, if there are no mistakes, you're going to stop running the algorithm. New example comes in, you've not made mistakes for a million examples, new example comes in and suddenly you make a mistake and you update. So you now have two weight vectors, one after the update and the other one just before, which has survived a million examples without making a mistake. Now the question to think about is, which one of these two is better? Is the one that you get after the update better because you've made an update, or is the one that survived a million examples without making mistakes better? Yes.
I would say the one before, since if you're counting on the data that you trained on and that it models the real world, then that's the vector that's going to model
right.
the real world better.
Exactly. And so, do people agree? Yes.
Is there noise in this data?
Possibly.
Okay.
In fact, quite likely.
Alright, well now I agree with this statement.
So let me just paraphrase what you said, and I agree with that as well. This weight vector has survived a million examples, which means you expect it to be more robust to future examples. Because you expect the future examples to have the same distribution as this one. Possibly there might be noise. How do we take advantage of this? And one answer is, you don't return the final weight vector. At every step, You just don't, you remember every weight vector. Every time you see an example, you remember the weight vector. Whether you make an update or not, you remember the weight vector. And you keep track of all of them. So if you got a million examples, whether you make a mistake or not, you have a million weight vectors. And at prediction time, finally, after this learning phase is over, what you do is you run all these million linear threshold units on the new example and take a vote. Weight vectors that survive more will get more votes. Right? You see is that clear? So let's say you keep track of every weight vector as you learn. And let's say for every weight vector, you keep track of how long it survived without an update. How many examples it survived before it encountered a mistake, before it made a mistake. So you keep track of all unique weight vectors, let's say. And when at prediction time, at test time, when it's deployed, instead of using just the last one, what you do is you use all of these things and give the weight vector, give the classifier a vote. Every classifier gets a vote whose weight is equal to the number of examples it survived. Yes?
What's typically the dimensionality used on that?
Let's say 1 million.
That'd be a lot of memory.
That's a lot of memory, yes.
Should the voting done at the training stage?
No, not at training stage.
You could have faced more examples at training stage than...
No, but not at training stage because I say so. For now. Yes?
I have a question in general on online algorithms. So we're talking about training a classifier on a batch set.
Yes.
Isn't kind of the advantage of an online learning algorithm that it can get better as it sees data in the real world,
Yes.
not just after batching?
Sure. Yes. And that actually is a subtle point because if your data is drawn from an IID distribution, independent and identically sampled from the real world, then a batch is good enough. But if you believe that the distribution of your data keeps changing over time, then you want your classifier to keep adapting to this changing thing, then online might be better.
Like changes in linguistics, for example.
Well, in fact, that's exactly what I was thinking of. Yes.
I think there is a probability is the W in different index have the same value.
Quite likely, yes.
Yeah,
That's possible.
so what should we do? We just combine them?
No, in this case,
Uh-huh.
I'm not done. So in fact, the point that you raised is actually an interesting one. If you have million dimensional weight vectors and you have to store 1 million of them, that's a ton of space. So gonna give us some grief very soon. But did I see a hand up here? No. Okay, so this version of the perceptron algorithm is called the voted perceptron. And in general, this style of learning is called voted, or this kind of a classifier is called a voted classifier, where you keep track of every classifier that you encounter during learning and keep track of how successful they are. And at deployment, you give all of these guys, you form a giant committee of classifiers and give all of them a vote as to based on how successful they are. This is called voted classifiers, and it turns out this kind of a classifier comes with a very strong generalization guarantees in terms of what is called pack learning. In terms of future performance, voted classifiers come with guarantees that they will do well on future data. We haven't touched pack learning yet, so for now let's just say that they come with strong generalization guarantees, which is the good news. The bad news is that this is a nightmare to implement because there isn't enough memory in the world to keep track of every weight vector that you can ever encounter. So a compromise is called the averaged perceptron. The average perceptron is an algorithm where you try to get the best of these both worlds. You want to store, you don't have too much memory. So what you do is instead of keeping track of every weight vector that you've ever seen, every time a new example comes in, whether or not you make a update to the weight vector, you update your running average. You keep a running average of weights, and you keep going on. And at the end, you use the averaged weight vector rather than the one that you actually train. So this is very widely used, and just to write this down as an algorithm, all you do, so first of all, if this step was not here, let's say this was not here, this was W. This is exactly the batch perceptron that I had before. You run multiple epochs over the data, and you keep updating the weight vector. Average perceptron simply says, whether or not you update the weight vector, you add it to the running average. You initialize the average to 0, and you add this the weight vector to this running average, and at the end you don't return W, but you return A.
How is that the average if you're just, it's more of the sum?
Sure, you return A divided by number of, so you can return A divided by the number of times you added these things. But it doesn't matter because end of the day I'm only going to take the sign of A dot X. And it's the same. In practice though, it might be a good idea to actually do this because so that you don't hit infinities because you keep adding these numbers. Is this algorithm clear? So this is called the average perceptron, and you could try this for your homework. I'm not sure if I asked you to implement the average perceptron, but it would be typically in almost every case that I've seen, using averaging improves performance irrespective of what the data is, especially in cases when there is noise. If there is no noise, everything is fine because even the vanilla perceptron would work. The interesting case is when there is noise in the data. So, yes?
Yeah, I think the initialize of W will in fact the average bit, because I think if the W is too far away as the perfect one, the average will just...
Oh yeah, sure, but then it won't, if you run this for enough epochs, it will get, the first one that was really bad will disappear in the average. The average perceptron, interestingly, does not come with the same theoretical guarantees that voted perceptron did because of that point. It does not have the same theoretical guarantees, but empirically it works really well. Yes?
So, could you use a different algorithm here besides, so we've kind of got like this online algorithm and now we're applying it to like a batch scenario. Could you use like linear programming or something?
Aha, that's actually an excellent point. In fact, there's a way of deriving a classifier without doing any of these things and just writing it as a linear program.
But it maybe wouldn't be as efficient or as higher.
Oh no, it does not. There are worse problems with doing that. Let's take this offline. Partly because that requires me to talk about quadratic optimization. But that's an interesting question, and in fact, I encourage you to think about it. So let's talk about couple of practical issues here. This is the easiest version of average perceptron. The one on the slide is the simplest one, and it has actually one really annoying property, which is whether or not you make a mistake on every example, you have to update this average. And if your vector is a million-dimensional dense vector, then you're paying a pretty heavy computational cost at every step, whether or not you make a mistake. I'm not going to tell you how to solve that problem. All I'm going to say is that there's a very cute programming trick that you can use to basically move this addition into the if and do some post-processing and get the exact same result. I'm not going to give away the answer. Think about it. Try to come up with this. It's a nice little puzzle. It's not very hard. It's widely used, and most of the time when people say they use the perceptron algorithm, actually this is the version they are talking about. And if you want to use the perceptron algorithm in the future, I hope this is the one that you will implement, because there is really very little additional effort that you have to do, and you get a lot of you get better generalization guarantees.
Sorry. When you're talking about moving it into the if, would you get, does it help your learnability when you are using the average when you're checking in that if?
No. Remember that the way the average perceptron was derived, it came from the weighted perceptron. The weighted perceptron, you want to keep track of every weight vector that you saw. So the average is basically like the sum of every weight vector that you've ever seen.
Okay.
So the average is pretending to be that committee that we cannot create. And when I said moving this into the if, you can't just naively move this in. You can't just put a tab here. So /t is not going to work. You need to do some massaging of these things so that the final result is identical. Was there a question here? Yes.
When you said move it into if, do you mean if there isn't an update, we shouldn't add the W to A?
No, not. That's what I said. I want the final result to be the same, but I want to update something like the average only when there's a mistake. So you only notice that you have to you have to keep track of a counter basically. Instead of making in addition to just this, you have to keep track of a counter. I don't want to give you the answer because I want you to think about it.
Yeah, because I think if we didn't move it into if, the one that doesn't have update, it means it survives.
Yes, so you have to somehow keep track of that using a counter somewhere. And do some post-processing at the end so that the final answer is exactly the same. Okay, enough about programming puzzles. Let's talk about another variant of the perceptron algorithm called the margin perceptron. And this is something that you guys will be implementing. The margin perceptron is, the story of the margin perceptron is the following. For the perceptron, vanilla perceptron or the batch one, what you do is you check for a mistake. And the way you define mistake is if y and the dot product, y and w transpose x, have different signs. Or equivalently, if y times w transpose x is negative, is less than 0. So if it's less than 0, you call it a mistake. If it is greater than 0, you're okay. Now, what you think about is, okay, so let's say it's greater than 0, but it's just this tiny number greater than 0. It's 0.00001. Is that a mistake or not? Is that probably it just happened to be on the positive side by random coincidence, but really it's too close to this margin. So you want to update even then. And this intuition leads us to this idea called the margin perceptron, where you don't check for negative, even if y times w dot x is positive, but smaller than some number, some eta, which is fixed and another hyperparameter, then it's okay. Even though it's positive, that means technically it's not making a mistake, and yet you update the weight vector. Because this is like saying your classifier is not very confident, so let me do the update anyway. Okay? This is only during learning. At prediction time, you still do the same thing. You still always check for the sign of w dot x. This eta parameter only applies at training time. And it's a hyperparameter, it's another hyperparameter. So we have three things now. We have the learning rate, we have the number of epochs, and we have this margin. Okay? And then, I know what your question is, so what's yours?
Mine goes back to cross-validation.
Okay, so it's the same question.
Oh.
Yes.
You already know what I'm going to ask then.
Yes. Go ahead, ask it.
If we have 3 hyperparameters, how does cross-validation work? Do you find the lowest for, let's say, learning rate, and then using that, you find the best for learning rate?
So let me tell you, okay, so this is related to your question, so let me answer the same thing. So we have 3 hyperparameters. So let's say we have the learning rate R, we have what was that, T, and now we have eta. So let's say that I'm going to pick learning rates from this set. It's going to be either 0.1, 0.01 or 0.5, one of these three things. And let's say t, the number of epochs that I'm going to run can be either 10, 20 or 30. And let's say the margin can be half or 1 or 10. Typically, let's not say 10, let's say this three numbers, some numbers. So I have three possible options for each hyperparameter. What you do is you consider one value for each hyperparameter. So you pick this one, and say this one. You have you have all the inputs you care about. Now you do 5-fold cross-validation. Find the average cross-validation accuracy. Just remember it. That is the cross-validation accuracy for these three hyperparameters. Then you pick another hyperparameter. Then basically you do grid search. You try the cross product of all these things, which is hopefully a small number. You have to. This is the number of things that you do cross-validation is limited by the amount of compute you have. So you try all possible combinations. For every combination, you get the average cross-validation accuracy, and then let's say the best one, the combination of hyperparameters that gets the highest cross-validation accuracy is these three. That is 0.1, 0, 30 and 1. Now what you do is you go to your training set, train your classifier using this setting of hyperparameters on the entire training set, and you get a classifier. Now that is the classifier that you're willing to sell. That's the classifier that you think is going to be the best classifier for the future because it has the highest cross-validation accuracy. Does that answer both of your questions? Not yours.
Well, mine, there's an extended question I have to this. During our homework, you have us run this for many different dimensional data sets.
Yes.
Do you want us to do cross-validation per dimensional?
For every data set is different. If you add a single feature, you have a new data set. If you do some normalization, you have a different data set. So cross-validation you should write cross-validation when you're implementing it in a general enough way so that it can account for all these changes. Every time you change anything, you have to do cross-validation again. So the experiments that you guys are running are actually fairly large. The amount of code that you're writing is going to be small, but your runtime is going to be quite heavy.
As a measure of incorrectness, should we be normalizing the weight vector so that you can measure how far, like absolutely, it's away from the hyperplane?
No. There's only, at least in the game that we are playing now, there's only one objective measure of incorrectness. How many mistakes does the classifier make on the test set?
But now we're applying a margin.
That doesn't matter. Still, it's the mistakes that count. Because once you have deployed a classifier, it doesn't matter. The distance from the hyperplane, though, is actually an interesting surrogate for the confidence of your classifier. And sometimes that actually gets into play. When you care about if a point is far, far away from a hyperplane and it's on one side, then you're more confident than if it's very, very close, because if you slightly change the weight vector, it might change the decision. But if it's far, far away, probably it's more robust. So the distance from the hyperplane is a surrogate for the confidence, but at least for the setting that we've been playing so far, the only thing of interest is the number of mistakes. Other questions?
Over here.
Yes.
I don't know if someone's already asked this, but can you combine average and margin?
Yes, absolutely. You can combine average and margin, you can combine average, margin and the batch, and any other variant that you can think of. They're all orthogonal things.
Is the epoch thing a sort of cross-validation, or is epoch to be implemented right with the algorithm?
It's part of the algorithm. The cross-validation takes a learning algorithm as input and it doesn't care what the learning algorithm is. And the batch perceptron is one learning algorithm. Okay, so I think we've come to the end of the rather long and extended discussion on the perceptron algorithm. So let me very quickly summarize where we are. Even though it's called Summary of Perceptron, I want to also summarize the idea of online learning, because we're going to continue on that thread a little. Online learning is this game where your classifier gets to see one example at a time, and whether or not, based on whether or not it makes a mistake, it gets to update the classifier, update the hypothesis. The Perceptron algorithm is probably the most dominant online learning algorithm, perhaps the oldest of this family, and it's rather simple to implement. All you need is vector addition, vector addition and dot products, and you're good. It's an additive update rule, and this is going to be important in the next 3 minutes. Additive means your updates are either you add or subtract to the weight vector. There's a very cool geometric interpretation of the Perceptron update. It simply says that it rotates the weight vector. Every update rotates the weight vector so that it gets slightly more correct. The Perceptron algorithm has a mistake bound, and you should know what the mistake bound is. You should be able to derive it. You should understand it. And the mistake bound simply tells us that this algorithm is a mistake bound algorithm. And it tells us that if the data is separable, the Perceptron algorithm will find the right separator. There are many variants of this algorithm, and there are some are more popular than the others, and I think I've covered at least the more dominant variants. You should be able to implement the Perceptron algorithm. You should be able to implement it, play with it, and hopefully the homework will give you a better feel for this algorithm. If you haven't, if you haven't started yet, hopefully you'll start soon. Yes.
You said that each update basically rotates the weight vector.
Right.
So it's possible that after several updates we have rotated the weight vector with 360 degrees.
Possibly. Yeah. It rotates and translates actually, but yeah, sure. Let's just say rotates, yeah. It's possible, but it doesn't matter if the data is separable, it's okay. You might get back to the same place. Actually, if you get back to the same place, chances are the data is not separable. That's the cycling theorem. You'll keep coming back to the same point again and again.
For cross-validation, are we to run the algorithm on each subset and average the resulting weights?
Yes. Oh no, you don't average the weights. You only average the accuracies. You do not average the weights. Every run is independent, and in fact, this is one of those trivially parallelizable things. Okay, so that brings us to the end of the Perceptron lecture. And if there are questions, please come to the office hours and all that. And I expect you to know this algorithm really well. Since we have half an hour, I'm going to try see how far we can get into the next learning algorithm, which is another. I've already given you a hint as what's the difference. Perceptron algorithm was an additive update rule. We're now going to look at another online learning algorithm called Winnow, where the update rule is multiplicative. This is an important family of algorithms. Unfortunately, not as popular as the Perceptron algorithm. I'm not sure why, because it keeps getting rediscovered again and again. Every decade, somebody rediscovers this algorithm. So, just to step back, where are we? We are still looking at linear classifiers. The Winnow algorithm is another algorithm that learns a linear classifier. We're still in this regime of mistake-bound learning, where we are going to define learning or learnability of a problem by counting the number of mistakes. The data keeps coming in a stream, and we want to, eventually our goal is not to learn a classifier or anything, our goal is just to stop making mistakes. And we've seen the Perceptron update rule. I'm not going to talk about it too much, but I do want to point out it's an additive update rule because this thing here is a plus. So you're updating using addition. We're going to move from additive update rules to something called the multiplicative update rule and look at the Winnow. And just like the Perceptron, I'm first going to present the algorithm, then derive its mistake bound, and then talk about some variants. So let's look at the algorithm. The setting is the same, and this time I'm using theta for the bias, and I'm explicitly showing the bias because it makes writing down the algorithm easier. We are still in the world of linear threshold units. So the classifier is completely defined by a vector w and a number, the bias, which I have called theta here. And the way that after learning or at any point, the way the classifier is used is if w dot x is greater than the bias, then you say positive, else you say negative. And the perceptron algorithm has a mistake bound which is r squared over gamma squared. At the end of the last lecture, I asked some of you to, or I asked all of you, I'm not sure if any of you did it, I asked you to prove to yourself that r square for Boolean functions is equal to n. Cannot be more than n for n-dimensional Boolean functions. Why?
The longest vector would just be like a string of ones.
Exactly. So, what is r square? R is the radius of a circle or a sphere that holds all the data points. And it should be centered at the origin. If you are in the world of Boolean functions, the farthest point from the origin is a vector whose every element is 1. So 1, 1, 1, 1, 1. And you compute the distance of that point from the origin, it is root n. In 2 dimensions, so if you have, this is 0, 0, this is 1, 1, this distance is root 2. And in 3 dimensions it's root 3, in d dimensions or n dimensions it's root n. Which means r square is n. What that means is for Boolean functions, the perceptron algorithm will make roughly n mistakes or O of n mistakes, n over gamma square mistakes. It can't make more than that. But here's a question that led to the discovery of the Winnow algorithm. Suppose you know that even though you have n features, only k of them are relevant. And this is actually not a very uncommon situation, because typically what we do is we throw in as many features as we can into the learning problem and hope that the learning algorithm picks it up. We don't know what's a relevant feature or not. And in fact, this is a particularly insidious problem in natural language processing, for example, where the dimensionality of these data vectors is in the order of millions. And we have no clue which features are relevant. We just throw it into this black box and hope it works. So suppose we know that only k of the features are even relevant to this problem, and k is much less than n, can we get a learning algorithm that is more dependent on k and not so strongly dependent on n? That's the motivating question. And in fact, this was the challenge that was answered in a constructive fashion using the Winnow algorithm. So let me give you an example just to highlight this point. Say we have a function which is only a disjunction of 2 inputs. So we have, let's say, 1,000 variables, x1, x2, x3 and so on till x 1,000, but only x1 and x2 are relevant, which means the function, let's say, is x1 or x2. But we don't know that. We have 1,000 variables. One algorithm that can learn these things is what we call the elimination algorithm, and I don't know if you remember it, so I'm going to walk. It's a very simple algorithm. What you do is you start off with a guess of the function. You start off with this guess that the true function or your current function is h of x, which is the disjunction of all possible Booleans that exist, 1 to x1 through x 1024. And a new example comes in. Let's say it is x100 equals 1, x300 equals 1, and the label is negative. What you can do, here's the learning algorithm, the label is negative, which means neither x100 nor x300 are in the function. So you just drop it. So now you started off with 1024 elements in your disjunction, you have 2 less. So you keep eliminating till you only have the 2 variables that you have that are in the function. This method can never make a mistake on a positive example. Why? What will happen if a positive example comes in? What will the prediction of this function be? 1. can it ever predict -1 on a positive on an input that should get a positive label? So let's take an example. The true function is x1 or x2, and a new input comes in, which is x1 equals 1, and let's say x100 equals 1, and the function is x1 or x2, which means x1 is true, which means the function is true. So f of applied to this equals 1, right? H is this function. It has x1, right? Which means it will say 1. It cannot say false to any input that has the relevant variables. Is that clear? But that's just a side point. What this means is, at most, if you have n variables, in the worst case, this algorithm will make O of n mistakes. It can make up to n mistakes, because it can eliminate every mistake will eliminate at least one of the bad variables, and there are only n variables in all, so the number of mistakes has to be less than n. So it's linear. This is just like the Perceptron algorithm. You have n bits. The elimination algorithm has a similar sort of a mistake bound. But this is kind of annoying, because we know that our function has only 2 relevant variables, and yet we make 1,000 mistakes. Wouldn't it be great if we can get a mistake bound that is dependent on the number of relevant variables? It turns out we did see an algorithm that has a logarithmic dependence on the number of functions. The halving algorithm. The halving algorithm makes how many mistakes? Log size of the concept class. So all we need to do is count how many k disjunctions, in this case 2 disjunctions there are. Right? The number of 2 disjunctions is, you have 2 slots or this, and here you can put x1 or x2 or any of these things, and here you can put x1 or x2. Or it can be negated, so it can be not x1, any of these things here. So you choose 2 variables, and then for each of them you can assign a positive or negative sign. So the number of 2 disjunctions is, or the number of k disjunctions is n choose k times 2 power k, which is roughly n power k 2 power k, and we've done this exercise in the past, so I'm not going to labor this point. The halving algorithm has a mistake bound which is k log n, which is only logarithmically dependent on the dimensionality. The elimination algorithm is an algorithm that is linearly dependent on dimensionality, and so we would like, in theory, we could use the halving algorithm. Can we? Why can't we use the halving algorithm? So we have an algorithm that is good, and it only has a logarithmic dependence on the input size, on the dimensionality. Yes.
Computational costs?
Yes. The halving algorithm gives a proof of existence. It does not tell us that there is an efficient algorithm here. Is the point clear? Or the mistake bound that the halving algorithm produces gives a lower bound. It tells us that you will make at least these many mistakes, but it does not tell us that you will make these many mistakes in an efficient algorithm. So what we would like is the best of both worlds. We want to make logarithmic number of mistakes, and we also want an efficient algorithm. Just like we did for Perceptron, it turns out linear classifiers are a good hypothesis class here. And it turns out that just changing the updater will give us this theoretically optimum mistake bound. And the core idea is quite simple here. Instead of adding weights, you just multiply elements of the vectors together. Wherever is a mistake. But before we get into the Winnow algorithm itself, is this argument clear? Is this the line of reasoning? Does it seem sound? And you're free to say no. let me quickly summarize the point. We are in this regime where the number of relevant features is very, very small compared to the total number of features. The perceptron algorithm and in fact the elimination algorithm will make the number of mistakes these algorithms makes is a function of the dimensionality, which is potentially very large. What we would like is an algorithm whose mistake bound is weakly dependent on the dimensionality, say logarithmically. One such algorithm is the halving algorithm, except the halving algorithm is computationally nasty. So what we want is an algorithm that can get the same number of mistakes, same mistake bound as the halving algorithm, and yet can be computationally efficient. And the answer to that is the Winnow algorithm. Is that? Yes?
So the difference in the setups between the previous Perceptron and this algorithm is that we're looking for the smallest subset of features that is still true. Whereas before we were just assuming they're all important and we're going to use all of them.
Possibly, yes.
So the dimensionality is not just the number of features, but it's also every combination of features?
No. The dimensionality is just the number of features.
Of the concept space.
So the way to think about it is you have a bunch of features and the only features that are relevant to the problem are a very small subset of that. So for example, if I throw in, let's take that example that we had from natural language processing where you have to decide whether a word is correctly spelled or not. Middle Eastern desserts or Middle Eastern desserts. And you use a feature that is just all the neighboring words. Previous word equals Eastern, next word equals R. And you get a bunch of sentences, the number of features you have is basically the size of the English language vocabulary. But most of them are irrelevant, right? So you don't want those irrelevant features to affect your mistakes, your mistake bound. And you only want your mistake bound to be dependent strongly only on the relevant features.
But it turns out K is really big. This is worse.
Oh yeah, absolutely. K is in bad shape. And in fact, that's the gamble we are taking. Yes?
Will K end up being a hyperparameter?
No, K is going to be a mystery thing that we don't even know. It's just going to show up in the analysis. It's like gamma. Gamma is, the margin never showed up as a hyperparameter, right?
So K is not some parameter that Winnow takes and says, okay, I'm going to optimize this for this many assumed.
No, that's a good point. So in fact, I think that also tells me that you're hungry for the algorithm. So let's look at the algorithm. And just like Perceptron, I've decided to just vomit the algorithm on a slide and then step through it. The setting is very similar but not identical. You have n-dimensional. I'm giving you a version of the Winnow algorithm that's a simpler one than the most general case, mostly because this is easier to analyze. And a bit of history, this algorithm was introduced in a paper by Nick Littlestone. It's actually one of the better machine learning papers that you will get a chance to read, so I encourage you to read it at some point. So inputs, for now, let's pretend that inputs are only Boolean vectors, 0, 1 power n. This means we are talking about all bit vectors. Inputs can only be bit vectors. And the outputs are true or false because we are doing binary classification. In Perceptron, we initialize the weight vector to 0. Now what we'll do is we'll initialize the weight vector to the vector of all ones. Weights are still allowed to be not Boolean. They are real value. So you initialize it to all ones and you initialize the threshold, the bias, to the dimensionality, to n, the dimensionality here. This is an online algorithm, so I need to define two steps. One is prediction, the other one is update. Prediction is identical. You take the sign of you take the dot product of your weights with the input, you add the bias. In this case, you're subtracting the bias, but it's okay, it's the same. So you add the bias and you take the sign of that score If the score is positive, you say yes. If not, you say no. And the update is different though. If the true example, the true label y is positive, in this case, if the true label is positive and the prediction is negative, what you do is you go element wise in your weight vector, and all the features that were present in the input, the corresponding weights, you just double them. Okay, and I'm going to step through this algorithm with an example, so we'll have multiple opportunities to see this. If the true label is positive and the predicted label is negative, you promote all the features that made this example positive by multiplying them. And if the true label is negative and the predicted label is positive, you just do the opposite. Every feature that is relevant, that in this example gets penalized by getting demoted. And you keep doing this. Yes.
For this algorithm here, you put down, you initialize your weight vector as ones.
Yes.
Beforehand, you taught us what Perceptron we do at zeros, and with the homework we see that doesn't really matter as long as it's the range from negative 1 to
Here, because it's, okay, first of all, because it's multiplicative, you cannot do it, you cannot initialize with zeros, because if you multiply or divide by anything, it's never going to change. Initializing with ones is convenient because it lets us analyze things better. And in the absence of any information, this is just like a zero. You are not giving it any information. Every feature is equally important.
Okay, thank you.
So let's step through an example just to make this more clear. And I hope is this visible at the end? Or the subscripts and all the tiny fonts? Because there's going to be a lot of stuff on this slide. So let's say the true function is a disjunction of 4 things: x1, x2, x1023 and x1024. These are the only 4 relevant features. Everything else is irrelevant, but we don't know. So to start off, what we do is we'll initialize our weight vector to all ones and the bias to the dimensionality, which is 1024. An example comes in. Let's say the first example that comes in is the example with all ones, and it turns out it's a positive label. Not surprising because it's a disjunction, but let's not go there. Now you first predict. The way you predict is your current W is all ones, so W transpose X is is 1024 because W is all ones, X is also all ones. And you know that 1024 is greater than or equal to theta, which is also 1024. So you predict positive, so there's no error. So you don't update the weights. Okay? This is the case where nothing happens. The next example comes in. This is an example, let's say, of all zeros. And again, you compute W transpose X. Because every feature is a 0, W transpose X is 0, which is less than 1024. So you predict -1. So there's no mistake. So you don't touch the weights, you move on. Another example comes in. Let's say it has a bunch of zeros in the beginning, except let's say that all the relevant features 1, 2, 1023 and 1024 are all 0, everything else is 1. I'm just randomly picking examples. So the number of, so there are some of Wi times xi is the number of, because every weight is 1, it's equal to the number of non-zero entries here in the input. And I said that all the relevant features are 0, which means the number of non-zero entries is 1020, which is less than 1024. So the prediction is -1, which matches the true label, so no updates. And you keep going on till no mistakes are made. Let's say a new example comes in and we make a mistake. So this time, only the first feature is 1, everything else is 0. So W transpose X equals 1. right? Because all the other features are 0, only the first element of W and the first element of the previous W, and this one R1, which is less than 1024, which means you predict -1. But we see that the true label is +1, so we made a mistake. The update rule demands that all the features that are in this input should be promoted, which gives us this update. Only the first feature is in that input, so it gets doubled, all the other features remain the same. That clear? Okay? Another example comes in, let's make another mistake. This time we make another mistake on a positive example. Our current weight is this, on top, and the input is this, so only x2 is there in the input, so the prediction, the score is 1 minus 1024, which is less than 0, so the prediction is -1. We made a mistake, so we promote the second feature, so the resultant weight vector gets a 2 in the second entry, and this goes on. We keep doing this every time we make a mistake. We only promote those features that are in the input. Is the game clear? And we keep going on, and let's say we just to illustrate an example, a case of a demotion. Let's say we, after many steps, we get to a weight vector that looks like this. Okay, and we get a new example, and suppose for this example, all the relevant features, the first two and the last two, are off. And I don't even know what's in these dots. Let's just say that for this particular example, the sum of W transpose X is greater than 1024. It predicts it as positive. So what we need to do is demote all the features that caused this example to be positive. In particular, all the ones here. So we demote these two by just dividing by 2. Is the mechanics of the algorithm clear before we get into the proof and why it works and all those things?
So it's more so an algorithm for finding which features are important?
It's exactly that.
Okay. So
in fact, that's pretty much what's going on here. Okay. We are just, because we are working in the land of disjunctions, it just, if you keep doing this, eventually, in fact that's a good question, eventually you'll get something like what's not visible. You'll get a weight vector that has 1024 in all the relevant places and some smaller numbers in all the irrelevant places, such that all the irrelevant things cannot gang up and push the example over the threshold. Is this idea clear, the multiplicative update? Okay. It turns out the multiplicative update is a really important algorithm in the history of computer science, and those of you who are taking the advanced algorithms class will probably see this, the same thing as well, where in that class it will be called the zombie binary search, because it has some interesting connections to binary search as well. It has been rediscovered again and again and again in machine learning, in economics, in geometry, in game theory, in operations research, and roughly every couple of decades we seem to lose this algorithm, and then someone comes up and says, aha, the answer to this is the multiplicative update. So it's important that you remember this, because chances are you'll be in something like that, because we eventually forget this algorithm if we believe history, and you can be the one that rediscovers it. And in fact, if you are interested, there's actually a very cool survey of multiplicative weight update algorithms. So I have 5 minutes left, and I'm going to try to give you a brief overview of the mistake bound that the Winnow algorithm has, unless somebody decides to take the next 5 minutes asking me questions. So you're eager to see the mistake bound. You know the algorithm, you understand it, you can implement it. Oh no, you don't.
Why do we use 2? You could just easily use 3 or something else.
Oh, that's an arbitrary choice, actually.
So just so you can multiply and divide.
Oh no, actually the reason for that is because when I derive the mistake bound, the proof is easy. The general version of this actually uses e power some constant.
Is it possible for things to get smaller than 1?
Oh, absolutely. Right? If you make a mistake on the first example and it's a negative 1, then you'll divide by 2, it becomes a half. In fact, if you keep making mistakes on negative examples, you'll basically, in expectation, you'll drive it to 0. It won't be exactly 0, obviously, but
Going off that, is the choice of 2 basically like the learning rate?
it's exactly like the learning rate. In fact, that's a very good observation. It's exactly like the learning rate. In fact, one way to think about a multiplicative update is if every feature were taken to a log space, then it becomes an addition. Then this 2 acts like a learning rate. Or actually,
We said that the prediction compares it to the dimensionality. So in that example, we had 10, 24, 10, 24. You know, in our prediction, all we need is one of those.
yes,
And
yes.
so then we get it wrong, right?
The function is a disjunction, right?
Oh, that's right, that's right.
If even one of them is good, then the Winnow is not just for learning disjunctions. In fact, it works for conjunctions just as well. It's a general purpose learning algorithm for learning. For the setting is you want to learn where irrelevant attributes abound. In fact, that might even be the title of the paper. Yes. So there are many questions. That's good.
Could you use this algorithm to determine if the data is linearly separable?
Why?
I don't know.
Why not Perceptron?
Good point.
So it's the same thing.
Okay.
So every feature that we consider relevant will be a feature where its value is greater than or equal to n.
Right. Because this is a disjunction.
Okay.
Only because this is a disjunction. In fact, here's an exercise. Right, here's an exercise that I don't want to walk through right now. Pick the same set of examples I had, replace disjunction with a conjunction. Or in fact, take a small conjunction and just randomly sample examples and see what happens, what the Winnow algorithm does. This is also a trivial algorithm to implement. So you could even just implement it and see what happens. For conjunction, what will happen is that the algorithm will settle on weights such that all the elements in the conjunction have to be true, have to be present. Only then can the weights add up enough to solve this. Otherwise, they won't. So in this case, you have 4 relevant variables. If you had a conjunction, it won't be. If you had a conjunction of those 4 things, you won't need 1024. You'll need only 256 because 4 of them add up. You get 1024. Are there other questions? Yes.
So can we reduce the dimensionality by ignoring those non-relevant features?
Actually, that's a pretty cool idea. In fact, the question is, do we care to do that? Because instead of doing that, what we could do is just learn the weight vector and now we are done. Right? We've got a classifier, we don't care about the dimensionality because only the relevant features are there. So, but in fact, this idea of putting a pressure on the learner to pick few attributes because we know that low dimensional weight vectors are good is a good learning strategy. The Winnow algorithm does this in an online kind of a constructive fashion, but in general this idea is a good one. To use the learning to reduce the dimensionality. Okay, I have a minute. Yes.
Geometric interpretation is like, instead of rotating the weight vectors, you're growing them.
You're not growing the entire vector, right? You're only growing along certain dimensions. So I don't know, the way I like to think of the geometry of this is that you're transforming inputs and the weights to the log space and then you're rotating in the log space. Because multiplication in the original space is like addition in log. That's how I like to interpret it, but you're free to think about it. Okay, I have about 30 seconds left. I don't have time to derive the mistake bound. I'm just going to give away the answer and then we'll derive it next week. This fits that bill. Its mistake bound is k log n. If you have k disjunctions and n dimensional, this algorithm will make no more than k log n mistakes, which is just fantastic if you think about it. all we have done is just change addition to multiplication, and it has this really cool property. We'll derive this in the next class, and I have office hours right now. If you want to talk about projects, please show up. And in general, project proposals are due.